decided to answer at least 3 questions from 32 questions too. So I decided to present this example about the vibro-acoustic of FGM circular plate. Sound and vibration are coupled sciences for talking about some concepts about coupled vibration with noise or sound and vibration, or to talk about mode shapes in modal analysis. Active control for reducing vibration displacements are another aspect for vibration control systems. The other science are more importantly for talking in engineering science about absorbing energies by optimal material for reducing acoustics for theater saloons or cinema saloons too. And also 2 famous and important methods and strategies for driving mathematical models in coupled systems such as vibration and acoustics too, are talking for finite element methods and boundary elements too. If I say about the applications of sound and vibration in engineering science, such as vehicle systems for reducing a lot of harsh sounds for passengers, in aerospace structures, also in aerospace cabins, in building acoustics for reducing a lot of systems, dynamical systems such as elevators or HVAC systems too, especially for air conditioning. Also for smartphones or laptops or other electronic devices to minimize vibration, maybe for increasing safety for users. And last items in applications in industrial machineries to improve workspace for workers. In this table, I try to compare FGM and BM methods in some factors such as complexity, computational cost, pre-processing, material behavior and application. In some items with the blue colors such as geometrical techniques, solve equation, mesh sensitivity, linear or non-linear material, and diversity. You can see between FGM and BM are some differences, big differences in using for material for the driving or modeling systems, especially continuous structure. For example, in this picture, we can divide 2 types of numerical methods, FGM and BM. In FGM, 2 variables are most significant designers especially, such as node and elements. So in FGM, the boundaries of the systems and the structures are defined for modeling in mathematical models. So BM are trying to model of the system, surround of the system, but in FGM is trying to model of the system for surface and volume in structure especially. So FGM or functional graded material properties are known with 3 types in power law, exponential or sigmoid function. These days, because of most diversities applications in engineering industries. So FGM materials are followed by so many industrial activities. So P is the general variables. So, for example, in power law distribution, the mechanical behaviors especially in stress to height or depth of the structure. For example, in these plots are showing mechanical behaviors of cantilever beam used by FGM material in power law distribution. So there is no linearity aspects. So FGM material conceptuality is a kind of non-linear material. So it depends on the depth of the structures, especially. For example, in sigmoid function, you can replace or substitute Young's modulus, density, and Poisson ratios to P. So at that time, for Young's modulus, densities, and Poisson ratios are defined based on the depth of the structures, actually. In my case, I try to industrial components are most useful to condition monitoring of the systems or health monitoring as a piezoelectric. So this is a piezoelectric sensor with electronic modules. We are focusing on about the structures of the sensors. This schematically diagrams and shapes of interior of the sensors by cutting from the middle of the structure. In the interior of the sensors, there are three sections. Firstly, is a copper or brass as a circular plate with the epoxy resin as adhesive material to cohesive of the Piezo-5. Actually, it's very famous to use. So on that time, piezoelectric material in the blue section connected with the metal section as a copper or brass. So sound pressures or sound flow, as you can see, are emission of the surface of the system sensors actually. So there is a bit hole is channel between sound flow and the sensor. So all of these are in this housing. So in the housing of the black cylindrical, you can see this sensor. The yellow section is copper and the white section is piezoelectric material. So about the degree of freedom, there are cylindrical coordination systems such as R, theta, and Z. So in FGM materials actually are defining about the two sections. Firstly, metal and ceramics. Piezoelectric materials is kind of ceramics, so I like to substitute piezoelectric in ceramic. So on that time, this structure is a composite material like FGM structure. So now I would like to talk about kinestitute equations, especially about the structural displacements and vibrational behaviors firstly. So I'm talking about finite element methods firstly. So based on Kirchhoff's law theory, we are driving displacements in 3 directions firstly. So after that, based on strain displacement, we are driving mechanical strain. So based on Hooke's law, we can connect between mechanical stress and mechanical strain based on FGM materials. So based on bending moments are these integrations for MR, N theta, and MR theta, and also boundary condition. I assumed these structures in the housing of the piezoelectric sensor is simply supported connections. So you can see W at the surrounding of the circular plate is 0. There is no displacement, and also there is no bending moment. So based on potential and kinematic energies, we are connecting between mechanical stress and mechanical strain too. So we can produce P and T as potential and kinematic energies. So behind of these, we can solve and extract K and M, stiffness matrix and mass matrix. So there are some matrices to calculate K and M. So in finite element, we have to estimate displacement in every direction by N. So N is shape functions of the each nodes actually. So this is the estimation for displacements by shape functions. These shape functions, S shape functions is meaning of the structural shape functions for just structure. And also acoustical shape functions are defined by some mathematical equations such as linear, quadratic, or higher order, as you can see. It's a finalization of the model to show vibro-acoustics of equations. So it's famous by the second law of the Newton equations. So it's a matrix, M matrix, M matrix, and stiffness matrix. So there are some external forces, moments, or other things. Vibro-acoustics actually are showing in these areas. So for these areas too, because we are defining flexural vibrations and pressure. So structural sections are defined by MS, KS, KSW, CS, and FS as external force. Acoustical section is defined by these matrices. So MS is SS, S-shaped functions, and MA is defined by A-shaped functions too. Finally, if we want to solve for free or force vibrations, it's well known. If you want to extract natural frequencies or shape functions, you have to use free vibrations. So on that time, Fs and Fa are zero. But non-zero is defining forced vibration in some cases. So finally, I want to talk about some coefficients such as alpha and beta in acoustical, structural, and acoustical sections. All of these are some defined by some approaches such as radio rates or especially experimental methods to calculate and using in these cases. Thank you for having me.